start with logistics, just like last time. So the exam is only over Chapter 20, Parts 1 and 2, not any of the magnetism stuff we just started today. It is going to be structured similarly to the first exam, where about 1/3 of the questions will be multiple choice conceptual type questions, meaning by points, so 30 to 40 points. And then the remainder will be calculation, mostly just because they take more effort to do. You can still use a cheat sheet. Whatever you want to put on one side of an 8.5 by 11 sheet of paper doesn't matter to me. There will be a bonus, and I believe that's it. For the length of it, I will try and trim it down. It's always a toss-up because I never know exactly how long it will take. It just depends on the person. So anyway, we'll see what it comes out to. The other thing about that, because on the survey, I saw a couple comments on that the exam was a little long. I think that's fair. The trade-off is that then I have to do less questions, each of which is worth more points. So that can work in your favor, but it can work against you if I cut the thing you knew and kept the thing you didn't. So it's always a balancing act. But anyway, so this first page is not really critical as far as knowledge. It's just to help you understand the goal that we were getting to in this chapter, which was handing things over from the detailed view, the electric field view, to the more averaged out, simpler view, the voltage, current, and resistance view, that typically people like better because it is easier to think about. It makes more sense. And that's me included. So I'm not testing on this page in any sense, including like what's the difference between a static and moving charge. I'm not testing on that. I just wanted to show what the difference was. This page is the first one where probably there's some content in here for exam questions. Specifically, conventional current is the thing that trips people up. So it is pretending that positive charge is flowing because that's just easier for our brains. And 9 times out of 10, that will have the same effect as the actual negative charge flow, the flow of electrons that's really happening. So questions like was on that last quiz. Which way is conventional current? It's the direction positive charge would or maybe even is flowing in a circuit. If it's like the quiz question, it would be something like, the electrons actually flow to the left. So which way is conventional current? And your answer would be to the right, because that's the direction positive charge would flow in that same scenario. Similar sort of thing for batteries. I wanted to tell you kind of what they do, but I'm not testing on that. And I'm not really testing on EMF or internal resistance. This page is the first one where like calculation kind of stuff becomes particularly relevant. And so I could ask something about how resistivity depends on temperature. The idea is generally that the higher the temperature, the higher the resistivity for most materials because it becomes harder for the electrons to move around in there. It's just they're knocking into all that stuff that's jiggling around from the higher temperature. And then very much I am likely to test on, do you understand what statement is being made here? And how it connects with this definition of resistance. So there's 2 ways we can think about resistance. This is how you would measure it. You apply a voltage across something and measure the current that flows through it. But Ohm's law says that resistance depends on neither of those things. It relates the two. This is just like what we saw for capacitors. The idea that they relate charge and voltage, but capacitance depends on more geometric things. Same goes with resistance. It depends on the length of the wire, the cross-section, and what material it's made of, which is what the resistivity is telling you about. So I could have you answer a question where you have to chain these 2 ideas together, these 2 different ways of writing resistance, and you have to find something that's missing about this object, like what's the length of this wire, or how thick is it, or whatever it may be. I give you enough information to find whatever that last thing is. In general, application stuff, I don't test on. It's just to tell you this has a point. But definitely these 2 questions, think of a mashup of them, that is likely. Power would show up in the context of a question about a actual circuit where you've got some series and parallel type stuff. I might ask you about the power dissipated by a particular resistor. The reason that can be tricky is this right here. We said that the voltage can't be whatever one you want. It's not the first one you see, which is usually the battery voltage. It's whatever specifically happens across the resistor you're looking at. And then the current can't be whatever one you want. It's got to be the current through that resistor you're talking about, because those are what matter for the energy that the resistor uses. I'll say more about that once we get to the more complicated circuits. Loop and junction rule, I could ask a conceptual question about just what do they say, but I'm more likely to bring up a calculation style question for them, like this. But again, the actual dividing line for the exam would be about here. I don't want you to solve for the currents. I don't want you to have to go through all of that because the physics is over once we get here. The reason I didn't include loop 3 in my dividing line is because technically loop 1 and 2 already tell you the information you find out from loop 3. To solve an equation with 3 unknowns, you need actually 3 equations, and we've already taken care of that with 1 for the junction and 2 different loops. But I mean, you're free to do a third loop if you want. All right, come back up a little bit. Series and parallel, I'm pretty likely to just go ahead and throw a combination one straight at you because it covers our bases. So I would say get this page very comfortable and the examples like it in the practice packet, and you will be in a good spot for the calculation part of this chapter. The thing that I see the most, and I've mentioned it a couple times already, that messes people up is they don't redraw the circuit every time they replace 2 resistors. They try and answer the entire equivalent resistance at once because they think they're so used to it that they can do that. Sometimes you can, and this is not my like boomer take of you got to do it my way. It's you miss things if you don't take it step by step. And with these kinds of problems, if you miss something early, it screws you up for the rest of the problem. For instance, say in the very first version of this diagram, I for some reason said these were in parallel. Well, once I combine them, that new thing is in series with this one, which is also not correct. And then you solve for a current, and that current you found is also not correct. And then when you work your way back up, that work is also not correct because you said it's the same V when it was actually the same I, or vice versa, because you combined in the wrong order. So these can really like topple if you're not very meticulous in doing them step by step. And I'll say more on that once we get to some of the questions I got. I think that's it. Someone sent in something about voltage dividers. I'm not asking you anything about voltage dividers. Again, applications I'm not testing on. I'm just telling you there's a point to this. And same here. That's the big stuff for this part of the chapter. Now on to part 2, which is instead of talking about resistors, we talked about capacitors. The confusing thing about them, which I said some of you already fell for my trap this morning, capacitance is charge over voltage. So you might think if I change the voltage, the capacitance changes. Nope. The charge changes. If I put 2 batteries across something instead of 1, I get twice as much charge on the plates. The ability of the plates inherently to hold that charge does not get any better just because you tried to squeeze more onto them. Its inherent ability to hold charge depends on its features, the size of the plates, how far apart they are, the dielectric. So anyway, that one today, hopefully you see what that means for what the answer was. I don't want to spoil too much for the ones who haven't taken the quiz yet. Dielectrics, specifically what they do is they weaken the field between the plates, and around them is really what's more important. We said the field out here is pretty weak for a capacitor. Sometimes we just pretend it's 0, but there is one, and that is where some positive charge is trying to get in, and these guys say, sorry, pal, door's closed, can't come in, unless the field they create is a little bit weaker, in which case maybe we could squeeze one more positive charge in. And that's the role of the dielectric, is to weaken that field so just a little bit more charge can squeeze in there. From there, we just derived the capacitance equation, so what it depends on. And this would lead to a very similar question to what I said about resistance. There's the way you measure capacitance, charge over voltage, but then there's the things that actually depends on area, spacing, and dielectric. But those are both valid ways of finding capacitance. It's just the idea of what does capacitance truly depend on. So you could chain those two equations together and find one of the things. So I give you the charge, the area, the spacing, and the dielectric. You tell me about the voltage, or I give you some other combination of those things, and you tell me about that. So this example right here is a good one, combined with this short little blurb we talked about of using those values to find a capacitance. Again, no applications. Absolutely 1,000%, I will ask one like these. It will be a multiple choice, like was on the quiz today. And I will talk through how you can kind of do this for any combination here in a bit. But it's me telling you how to do it for an exam, not how I want you to just know it forever. And okay, to be fair, you don't necessarily need to know this forever. But what I'm gonna say is like this way is the easiest way, the math way, but it tells you nothing about how any of this actually works. It gives you the right answer. And I will do a little bit more of that here in a bit. All right, energy stored in a capacitor. We'll go ahead and say that will not be on there. Just for this part, that's still a relevant thing, but everything else on this page, yeah. Series and parallel capacitance, I will ask about it too, but it is just about the same procedure as for resistors. The only difference is the rules swap. It's not a swap for the voltage and current stuff. Series means same current / charge, whatever thing you're talking about. Doesn't matter if it's capacitors, resistors, batteries, it's true for anything. Same with voltage. It's still the same for two things in parallel, no matter what they are. What I mean when I say that the rules swap is for resistors in series, we had that nice just add the numbers up. For capacitors in series, we have the reciprocal thing. And then for resistors in parallel, we had the reciprocal thing. For capacitors in parallel, we just add them up. That's the thing that swaps. And it is because this rule is a little bit jumbled compared to the Ohm's law / V equals IR sort of thing we saw for resistors. Because the charge-like thing, current, is over here multiplied by resistance, and then voltage is over here. For capacitors, the charge-like thing is on its own, and then the voltage is what gets multiplied by a number, and that's why all the algebra kind of flips over. Oh, and then again, no application stuff will be asked about. All right, I think that is a quick crash course recap. Are there any questions on this so far?
I think for me, what you mentioned earlier about how there are two ways to describe it, like with resistance, like you have Ohm's law.
Yeah.
And then you have like the one above. So like I just struggle to like understand how to describe it using those two different ways. And the same thing that goes for capacitance, like there are two ways to look at it and seeing what's fixed and what's not. So like the patterns, I guess. Like I understand Ohm's law and like how the slope is like showing the relationship, how it's constant. But then like putting it back into the formula, like resistance equals rho times length over area. It just I don't know how to not overthink that about resistance.
So in a conceptual sense or like just a calculation?
Conceptual.
Okay. Conceptually, the reason it doesn't care about voltage and current, but it does care about all those other things, is because voltage and current are things that are sort of forced upon it. You apply a voltage across a resistor and you see a current flow through it. Same with a pipe. You put a height difference between its two ends, or you put some pressure on it, and water will flow. But that's nothing that the resistor or the pipe has any say in, any control over. All they have a say in is how long am I? How wide am I? What am I made of? So those are the things that resistance truly depends on because it's a description of the pipe or of the resistor, not of what's going on around it. You can use what's going on around it to understand or find that value, but that doesn't mean those things determine it. Does that help a little bit?
Yeah. Is it like the water tower, how like it's not about the water, but the properties?
Yes, exactly. It's the
Okay.
same thing there. So you impose a certain amount of water you want the tower to hold, and that will go up to a certain level. But the tower has no say in that. All it has a say in is how wide am I? How high above the ground am I? What do I have inside of me holding all this extra water? And those are what innately determine what it can do, what it can hold.
Okay. That
Yeah.
helps. Thank you.
Mm-hmm. All right. Other questions from the folks that are here?
The only thing I had was just to go back over number 16 that was on the practice exam.
Okay. All right, let's start with that. Okay, yeah, this one's tricky. This is kind of a stretch problem. So those are the ones where I probably wouldn't ask something this hard, but it's like if you can do it, you know you're probably okay. So a set of light bulbs are connected in parallel to a 120 volt source. This is exactly like what's happening with your home outlets. You could plug in a bunch of different light bulbs in different outlets. They will all have 120 volts across them. Each bulb dissipates an average power of 60 watts. So that's power. This is voltage. The circuit has a fuse that burns out when the current is 9 amps or greater. Determine the largest number of bulbs which can be used in this circuit without burning out the fuse. The easiest way to do this one is with the loop rule, Kirchhoff's loop rule, because if we look, there's a loop with the battery in this bulb, there's a different loop with the battery in just this bulb, there's a different loop with the battery in just this bulb. And that's going to tell us a couple things. One is what I already said, they're in parallel, and so therefore they should have the same voltage across them, but even the loop rule tells me that because here's the rise, the drop for any of the loops must be 120 volts. And the only thing in each of those loops I just drew is a light bulb, so there must be a 120 volt drop across it. All right. Then I ask about this power thing. So power is current times voltage, and they're telling me about the power for each individual bulb. So they are telling me, hey, you know this, you now know this, it's 120 for each of these. You can figure out the current specifically through this light bulb, and it will be 60 watts over, what was V120? So that's 0.5 amps. That's what flows through each bulb. However many there may be. Because that's sort of like what they request. Sometimes you hear it called how much current a device draws. It's based on the inherent resistance of the bulb or whatever it is. But anyway, it's like they all request half an amp. The question is, can that be provided to them and up to what point? So they said the fuse can only handle 9 amps, but let's look at where these currents must have come from. So half an amp, if I trace it back to this junction, and half an amp went this way. So what must have come into that junction?
The same amount.
Yeah, so it would be 1/2 plus 1/2, so 1 amp is what went into that junction. And then it split into 2 halves. All right, I trace that back. 1 amp went this way, half an amp went the other way, so what must have gone in? So like I saw one person walk out this way, and this is gross, but half a person walked out the other way. How many people walked in?
1.5.
Yeah. And see, this is for 3 light bulbs. If I had a fourth, then I would have found that 2 amps is what I would get if I backtracked all the way to here. If I had 5 bulbs, I'd see 2.5 amps. If I had 6 bulbs, I'd see 3 amps. And so on and so on and so on. So how many bulbs would it take for me to see 9 amps flow?
Like 18.
18. So 18 bulbs for 9 amps. But they say that the fuse burns out if the current is 9 amps or greater. So I actually can't do 18. If I do 18 bulbs, then I will burn out that fuse. So the most I can do is 17. And that will be 8.5 amps. That will be safe. It will not burn out the fuse. Does that make a little more sense?
Yes, it does.
Okay. So that one is tricky, and it's kind of meant to be. It's a stretch. But this is also actually relevant for like a home. So if you look in your breaker box, you have fuses, and often they're like 20 amp fuses or 10 amp or 50 amp, depending on what room is being supplied. And what is happening, what you should imagine, is in that room, you're plugging in different devices, and each one asks for a different current. And that's all well and good up until a point. If this thing asks for 2, and this thing asks for 3, and this asks for 4, all right, we're at 9 amps. But if that's on a 10 amp fuse in your breaker box, if you connect even one more thing that draws more than an amp, it's going to trip the breaker, it's going to blow out that fuse, and you'll have to go replace it. So this is why you don't want everything running at once unless it's in a room that's the fuse for that room is designed to handle it. So like the kitchen, typically, you're going to have a lot of high current devices like ovens and dishwashers and that sort of thing. So they're on a larger fuse. I remember in grad school, I don't know what amperage that fuse was at in our like study area, but you could not turn on a coffee maker and a microwave at the same time, or you would trip the breaker. All right, let me come back to the chat. See that? Page 7 in 20.4. The idea on this page is, first of all, what is power? It's how much energy is delivered to something per second. So different devices, they need different amounts of energy per second to run properly. It's sort of like an Olympic athlete. They have to eat so much more than the average person because the amount of energy they're using per second to do what they do is so much higher. And if you don't keep handing them food at the right rate, they will conk out. They will not be able to maintain that level of exertion. Similar with electronic devices. Different ones for what they're doing need different amounts of energy per second. And so we ask, all right, what determines how much energy they're going to get? And you could come back to the food thing. Just imagine passing a bunch of plates to like an Olympic athlete. What's going to matter is how many plates you can pass them per second. That's like the current. And then the other thing that's going to matter is what's on those plates. So how much energy is there per plate? Are you giving them good stuff or are you giving them garbage? So is it a bunch of like chicken and rice or is it half a Pop-Tart? So current is again like the number of plates you can hand them per second. Voltage is like the quality of what's on each plate, the energy per plate. And that will determine how much energy you can get to them per second. Down here, that's just saying if it's specifically a resistor that you're trying to hand that energy to, it uses it in a specific way. It will always try and convert that electrical energy you're giving it into thermal energy. It will heat up and it will, in a sense, waste the energy. It's like you're handing it to someone and all they're doing is just like sort of throwing it out. But in a sense, that's sort of what an athlete is doing too, is like they're just heating their own body up, generating heat to accomplish something. I don't want to say that's useless, but it's like it's generating heat at the end of the day. Anyway, so these two expressions are talking about specifically a resistor because it applies that V equals IR relationship to say you could calculate it this way if you're talking about a resistor. This one is true no matter what thing you're talking about. All right, and then there was another thing. Okay, page 12 in 20.5, but all right, so the idea here is that that thing V equals IR, that's, the nice thing about resistors is they have a nice simple relationship, is it only actually applies to one resistor. So if we've got a circuit with more than one, what do we do? And the trick is pretend it is just one resistor. How do you do that? By figuring out how to replace resistors in pairs. So if you can pair them off and say, I know that these two are equivalent to one single one, you just keep doing that until you're down to one resistor left in the circuit, and now V equals IR works. Once you've done that, you work your way back up because you're gradually finding out the voltages and the currents for each resistor, and you can find whatever thing you don't know about them as you go back up. So specifically for this question, I look at this circuit and say, I have no clue about anything going on in this circuit except that this is a 24-volt battery and then the values of these resistances. What do? I just start to notice what could I combine. The one that stands out most is that these are in series because there is a direct path from one to the other. And I did see questions about like, how can you tell series versus parallel? I'll take another shot at that here in a little bit, but I'm just going to take for granted right now. Those are in series. So I replace them with one. And then I say, all right, we're doing better. It's only 3 resistors now. I still don't know how to do that. But these are in parallel. So let's simplify down again and say, all right, we're down to 2, looking pretty good. Now I see that these are in series. Okay, great. We're down to 1. This is a circuit I know what to do with. I know the voltage across the resistor. I know its resistance. I can find the current because this applies in this case because it's about one single resistor. And that gives me the current. And now I say, all right, I think I know everything there is to know about this resistor. The only thing that could be left is you could take the current you found, that 0.1 amps, and multiply by this 24 volts, and you would find that 2.4 watts is what's used by this resistor. That's what I meant earlier when I said I would ask about power in the context of a circuit. Can you use the currents and voltages you found to find the power? Or again, you could use I squared R or V squared over R. They will all agree as long as you did this right. Okay, but I work my way back up because I know currents for series things. But now I know the current through this resistor, so I could find the voltage across it. V equals IR applies because I know the current specifically for that resistor now. And so I find 11 for that one. I also know 0.1 amps goes through the other one because they're in series. There is no other way for charge to flow. And so I know the current specifically through this. I can find voltage. And I say, all right, I know about everything there is to know about this circuit. I take a step back. And it's just sort of saying, what can I carry back with me as I move through? And to answer that, you have to know, what do series things have in common? The current. What do parallel things have in common? The voltage. And it's just sort of a puzzle. You're unwrapping this as you go back up.
Confused about the going back up. That was the problem I was.
All right, well, I'll come back. I'll just redraw these then. Let me copy these and I'll just get rid of some stuff. So that's how I get my first thing, 0.1 amps. And now that I know the current through this resistor and the voltage across it, there's not much else to know other than that power you could calculate. So I'm ready to move on. That's how I know I'm ready, is I know everything. I know the current and voltage for every resistor in this picture. So I'm ready to move to the previous picture, and I have to ask what is okay to keep from the one I just finished dealing with. And since they're in series, what do series things have in common?
It's the same.
Yep. So that is okay to bring up here. It's still 0.1 amps through both of them. I'm not guaranteed that things in series have the same voltage across them. two pipes that you connect together don't have to be at the same height. They don't have to drop the same amount. But what is true if you connect them directly to each other is the amount of water flowing through each better be the same. But that still helps me because I now know that 0.1 amps goes through this resistor. I also know that 0.1 amps goes through this one. The only thing I don't know is the voltage drop across them. But that's okay. It's okay to use this because I know specifically about these resistors' currents. So 0.1 amps and 110 ohms. That'll come out to 11. That's how I get that one. 0.1 amps and 130 ohms. That'll come out to 13. That's how I get this one. Is that all okay? And so I evaluate. I say, am I done? I know the voltage across this resistor. I know the current through it. Yeah, I'm done with that one. I know the voltage across this resistor. I know the current through it. Yeah, I'm done. I'm ready to move up a level. And so I have to ask what is okay to keep when I move back up to this level. Well, what I had to do to combine these things was say they were in parallel. What do things in parallel have in common?
Voltage?
Yes, same voltage. And I say, all right, what voltage is that? Well, it's whatever I got for the combined version, the equivalent resistance, and it was 13 volts. So notice the 110, nothing has happened with it. It's still just what it was, so everything about it we already knew. There's no merging or splitting or anything that's happened for it. It's boring old self. But for these other two, that's where we had to decide what we can keep, and what we can keep is the voltage. It's 13. All right, I ask myself, what don't I know? I'm good on this one. It's already taken care of. It's the other two, and I would like to know the current through each. So I say, all right, V equals IR. What do? I want current. So current is V over R. And I need to do that for each of these two resistors. I'm being a little lazy with subscripts because I'm just kind of talking through it right now. It's 13 volts.
You're good. That's working.
And 180 ohms. And then this was 13 and 470. If I do this math, I get 0.072 amps. If I do this one, I get 0.028 amps. And so I now know 0.072 amps goes this way. 0.028 amps goes the other way. And it's not a coincidence that that adds up to 0.1. That is the current that had to split in order to let some of it go one way and some go the other. So then, yeah, finishing out, I just ask, all right, what can I carry up from here? Because I'm done with this picture. I'm ready to move to this final one. And it's this one that was actually an equivalent resistor. It was two in series, so it's the same current. And so I know I can carry that up. It's 0.028 amps. I'm not guaranteed on the voltage. And the other two are already done. So I use this current. I find the voltage across each. It will be, I think it was 6 point something.
6.1 and 6.9.
Yeah, and it is just, once again, V equals IR. And you just say, I want voltage now, so I'll just put in current and resistance. For capacitors, it's the same exact thing. It's just really the only thing that changes is what way you add them. So if you had series capacitance, you would do 1 over 220, 1 over 250. And then when you had parallel, you wouldn't do the reciprocals, you would just add. And when you're working your way back up, it's not V equals IR, it's Q equals CV. But then again, you solve for what you need. And then what can you carry up? If it's parallel, you can still carry up voltage. If it is series, you can carry up charge. In this case, makes more sense to talk about than current because capacitors hold charge. They don't want it to flow.
Could you just go back and explain like the direction that the current goes? Like
Yeah.
once I get the value, does it depend on charge like positive, negative?
It does. So typically, so the long end of the battery is what we call the positive terminal, the short end is the negative. It's very typical that current flows away from the positive terminal towards negative because that's what we said conventional current does. It's positive charge, it's going to move away from positive charges and then towards negative. From there, I know that it goes one of these two ways, mostly because it's kind of, I'm actually picturing something flowing between, like, to me, these wires are actually like pipes. The resistors just are particularly restrictive pipes. They're like really narrow ones. And so if water is flowing around this way and it reaches this branch where there's one pipe going one way, one pipe going another, what's the water going to do? It's not going to flow backwards. It's not going to say, we can't go that way, you guys. It's going to keep flowing sort of downstream, down towards negative. And so I can see that it keeps flowing through the pipes, flowing through the pipes, flowing through the pipes. Whereas up here, we said it's not going to do this. It's just going to keep flowing. And then right here, this would be like two pipes meeting that water is flowing from each of them. It reconvenes, it rejoins.
Is that the junction point when
Yes.
they meet? Okay.
Yep. So junctions are both where current splits and current meets back up. What matters is that it is where current can change into multiple different branches.
Also, last question, does the current go to the resistor that has like less resistance? Does it like prefer?
Yes, more current will flow through the lowest resistance, and that's where you get this idea that people say electricity always follows the path of least resistance. That's not true. What is true is the most current will flow along that path, but there will still be current along other paths, which is why it's not safe to touch things that are electrified just because there's something metal that's even less resistive than you. You can still get a decent shock when that happens because some current will flow through you as well. It's more like electricity flows across all paths. It's just easiest for it to do so in the least resistive one. And typically, you don't actually have to know this. I just do it to try and illustrate. You're just finding numbers. What you need to know is just that it splits in some way at these junctions. Something is different when you hit a junction. I'm looking at your questions, Eva. I think I've covered some of these. So it's more the capacitance stuff. Do you feel like the other stuff is covered?
Yeah, I do feel like a lot of it is covered. It's just conceptually for me, the Q equals CV.
Yeah.
That's where I do struggle, like what's going up, what's going down, especially if the battery's disconnected or not.
Yeah. Okay, so this is where I said I was going to give you all the general kind of rules. So let me just stay on my blank page and do that. Here's your key trigger words. If the battery is disconnected, charge is fixed. Reason being, the battery is the thing that pushes charge onto the plates in the first place. As soon as it's disconnected, it can't push anymore. It's not that the plates then just sort of freak out and all the charge flows back. What actually happens is that whatever you've got at the moment the battery was disconnected, so if you had whatever 4 units of charge means, if you had that at the moment you disconnected the battery, that's what you've got. That's all you've got. You can't get more on the plates because there's the thing doing the pushing is not there anymore. You also don't get less because these plates sort of help keep the charge on the other one where it is. Like the negative charge here attracts the positive charge on the other plate and vice versa. So they want to stay there more or less. If the battery is connected, it stays connected. Voltage is fixed. The battery can push more charge onto the plates, but only up until the voltage across them, the difference in potential, is the same as whatever it is for the battery. So if you've got a 9-volt battery connected across this capacitor, you're never going to see more than 9 volts between the two plates. It can be the case that when you insert the dielectric, because that actually makes a little bit more room for charge, you get a little blip in voltage, but that's a technicality. It eventually sort of re-equilibrates back to 9 volts. So that's just as good as saying it never changed from 9. So then the second piece is a dielectric inserted raises capacitance, a dielectric removed lowers capacitance. And the variance on that, because I don't have to just ask about a dielectric. I could say I make the plates bigger, because that also raises the capacitance. Or the plate's smaller, lowers the capacitance. So I can ask variance on this pretty easily, because I'm just asking, do you understand what trends are present for charge, voltage, area, all that sort of stuff? I'm going to leave it to you if you want to expand on that so you have your complete list for any scenario. I mean, it's okay to do that. But once you have this, it becomes easier to answer kind of any question. Say I remove the dielectric while the battery is disconnected. What happens?
The charge is fixed.
Yep, the charge is fixed. So,
And the capacitance decreases.
yep. So what must happen to voltage?
It goes up.
Yep. You have no idea why. There's no reason for this other than the equation says so, but it's correct. So the analogy version of this would be you've got a water tower. The amount of water in there can't change, like you've plugged it up so no water can flow in or out. But all of a sudden you shrink that tower down. You compress it down into a smaller tower somehow. What's going to happen to the water level?
Goes up.
It rises, yeah, because there's less room for the water to spread out. It can only go up, not out. Or the actual real physics is when you disconnect it from the battery and remove the dielectric is the thing that was keeping the electric field between the plates, the charges on them. It was keeping it weak. If you take the dielectric out, suddenly the field gets stronger again. The field is like the rate of change of the potential, so it's the voltage over distance. So the voltage also goes up. It's really that the capacitor is not as efficient at storing the charge anymore. It takes more effort, takes more energy to hold that charge without the dielectric in there. Let's just do a real quick one on this, just to see a different variant. Battery stays connected, but I make the plate smaller. What happens? All right, so I made the plate smaller. What happens to capacitance?
Down.
Down. All right, what can't change if the battery
Charge.
stays connected?
Voltage.
Mm-hmm. So on the right-hand side of this, you have one number went down, the other didn't change. What must happen on the left-hand side? Put literal numbers to this, like this is 5 and this is 2. 5 suddenly becomes 3. It drops to some lower value. What's 5 times 2 versus 3 times 2? Do you get a bigger or smaller number out?
Smaller.
You get it smaller.
Yeah, so you went from 10 to 6. So the left-hand side also goes down. What you get out when you multiply those two numbers, it becomes a smaller number. All right, and then page 6 on chapter 20, part 2. Got confused with the charge traveling over the capacitor, but the leftover charge shows it is attracted or repelled. Can you explain that one a little more?
Just like we start with A and then B, right? And then we go to C and D, like, and you were labeling it as positive and negative Q. I think that's what I got a little confused on.
Okay, yeah, let's talk through it. So the battery is the thing that we said lifts up positive charge, and then the positive charge will just fall back down naturally. That's what it would like to do. So we give this charge some energy, we lift it up to a higher potential, and then it starts to fall back down. But it can't really fall past this plate because it can't jump the gap between them. There's not enough energy, typically at least, for it to be able to jump over through empty air, empty space. So instead, what happens is positive charge starts to pile up on this plate. So far, so good?
Yes.
Okay, but now you've got a lot of positive charge on this plate. There is positive charge in this one too, but right now it's paired up with an equal amount of negative charge. It's a neutral plate initially. What's the positive charge on plate A going to do to the positive charge on plate B?
Attract?
So it's positive on positive.
Oh, repel.
Yep.
Repel.
Yep. So it pushes the positive charge on plate B away. That's what this is representing. What is left on plate B if we push some of the positive charge away?
Negative.
Negative. And the part you said about attract, that is true here. This negative charge is pulled towards plate A, it's attracted to it, and that's what keeps the charge sort of on the plates. It doesn't sort of reestablish neutrality or equilibrium when we take the battery away, because these guys still are like, no, I still want to hang out with the positive charge. I don't care that you took the pushing thing away. Now that we're here, we'll attract each other. But now let's focus on where does this positive charge go? It would still like to head towards lower potential, but eventually it piles up. It has nowhere to go over here. And that is sort of the confusing thing, is no charge moves through the gap. There is not actual current flow in here. And there is no like something leaps over. Instead, it's just that there already was positive charge on plate B to begin with, and it moves. But from the outside, if you're tracking that, it kind of looks like current and then current. It's just that in between, actually nothing flows, which is weird, I'll grant. But anyway, that positive charge moves to plate C. What's that do to the positive charge on plate D that right now is paired up with negatives?
Repel.
And that leaves negative charge on plate D. And that's how we establish the plus Q minus Q and plus Q minus Q.
Oh, so that's the charge at the end, like after it
Yes.
repels it.
Yes.
Oh,
This is
okay,
like
okay.
the final state of this circuit, because up until this moment, charge will flow and flow and flow and flow. As soon as we reach so much buildup of charge on these two plates that the total voltage across them equals the battery voltage, the battery can do no more. And in fact, everything just comes to a halt. It's like you've totally filled up two water tanks that are connected to each other. You can't squeeze in anymore, so no more water flows.
And on the right side of the capacitor, you said it's positive? Like they're, yeah. Like initially.
Yeah, so initially everything's actually neutral. These are just hunks of metal, and you've got equal amounts of positive and negative charge. The role of the battery here is to sort of upset that neutrality, to get more positive charge in some places and more negative in others. It didn't invent new charge, it just shifted it. It is a form of induction. It is a form of shifting charge, like way back when. We just kind of, I don't know, we just don't say it that way at this point for some reason. Okay, and then equivalent capacitance. Do you want to say any more on that, or you feel okay on that one?
We don't have to go over it in depth. I just wanted to understand why you said it's equal to, like, when we redrew it. Like, could you just explain that? But also, if anyone has any other questions, definitely feel free to ask. I really don't mind.
Oh, no, I mean, this is, I'm sure, the questions that a lot of people have. Everyone always thinks like they are the only one that doesn't understand this. Half the class doesn't understand.
I don't fully understand it either, but I just do my best with it. So don't worry about that.
Yeah.
Okay.
That's why I want y'all to ask questions because you're helping everyone. They just are too afraid to ask a lot of the time. And that's exactly the
Okay.
feedback I get on the surveys. I ask, why don't you ask questions? And they say, I feel like I'll feel stupid. And no one realizes that I get that answer 20 to 30 times on these surveys. Everyone is afraid they'll look stupid, which means no one should feel afraid because everyone feels like that.
I'm not really afraid of it, but I just suffer in silence type of person.
Yeah, well, I mean, you are taking charge of your education is how I feel about it. Um,
Yeah.
anyway, so on this one, it is kind of hard to see like how you know to redraw this like that. Is that what you're getting at?
Yeah.
Okay. So literally what I imagine is like take the whole chunk of this circuit that consists of capacitor 1 and capacitor 2 and then all the way up to whatever the nearest junctions are. So for capacitor 1, the nearest junction is right here and then over here on the other side. Capacitor 2, the nearest junctions are, in fact, the same junctions, which they should be because that's the requirement for things to be in parallel, is if you trace around, you should find the same junction from both sides. That's the pinch test, is another way of phrasing it. So imagine covering up that entire part of the circuit. Like, that's what I mean when I say slap a sticker on it. Like, let's try this. What's in there? I don't know, but it's equivalent to if there were just one capacitor in that box. You see what I mean? Like, we just reconnect at the two endpoints. My goal is to replace these two capacitors with one single one that does the same thing. And in a real world sense, this would be like you unplug these two capacitors from the rest of the circuit. You take them out and replace them with one single equivalent capacitor that does the same thing. Like imagine pulling out two and just putting in one single one instead. Well, where would you reconnect the ends of that new capacitor? It would be wherever you cut out capacitors 1 and 2 from. So you could imagine it that way. I cut them out. Like I cut the wire right here. And now say, instead of whatever that was, there needs to be just one capacitor between those 2 points.
And will it always be between the two junction points?
Yes, because that
Okay.
is like what makes two capacitors be in parallel. So I should say yes if they're in parallel. If they're in series, so if I come down to right here, I still think about like what would it look like to cut them out of the circuit? Cut capacitor 1 out, cut capacitor, I guess 3 out is what it was labeled. I need to replace them, all this junk. So I'll try the covering it up thing again. Replace everything in here with just one capacitor. And still sort of connect the lines so I make a complete circuit. And that's how I get this picture. Yay, nay?
Yeah,
Okay.
it's good.
And that actually leads me to another one because I got a question on this of recognizing series versus parallels of the slide thing and the pinch thing. That's just one attempt I'm making at trying to explain how you can tell because if I'm being honest, that's not what I do. My brain just sees it, and I think even when I first learned this stuff, for some reason my brain just sees it, and I think that is just I don't know, different things click for different people at different rates. That's not that someone's smart and someone's dumb. There's a different thing that you click for that my brain doesn't do right. So anyway, I just see it, and so I have to try and figure out what will help see it. The other thought I have for that is, how do you actually connect things in series in real life? So say I'll go back to resistors because you've seen them a little bit in lab, a little bit more. So you've got the color code on them, you've got the two ends. So the question is, how do I connect them in series? Series means one after another. And in a real world sense, if you needed to connect these, you would either kind of loop the legs around each other, bend them around, or you would solder right here, or you could wrap some tape around it. You join them at the ends in some way. What if I drew that schematically? That's series. And that's true even if I bend the wires. So instead of them being aligned like that, I can still connect them in series by joining like this. It's still the same thing. They're still meeting at that leg. And that's true for the diagram too. This is still series. What is not is if I had a third one right here. So in the real picture, I would have something like this. Why is it not? Because there's not just one direct connection between one and the other. There's a different path that charge can flow through in real physical space. And that eliminates series because series is supposed to be same current. This is a point where charge has a choice of which way to go next. Parallel, let me say a little bit on that. How do you actually connect two things in parallel in real life? You just twist the legs together. So here's my two resistors. If I want them in parallel, I would twist the legs together at either end. And now those two are in parallel. If I draw that schematically, it would look something like this, or again, because bending wires makes no difference. It doesn't decide that charge now flows a new way. It just sort of reshapes the wires a little bit. You adjust them to make this look prettier. So this is the same picture as if I drew it this way. I just sort of straightened out the wires on either end. That's parallel. Or if when I joined them, I had these legs kind of continue on, connect to other wires, and I just twisted the other one around that. So it's sort of like a, I don't know, I'm picturing like a monkey holding on to its mom, just grasping on to the bigger resistor, but it's still parallel. It's still twisting the ends together in some sense. And I guess that's why I just recognize it when I see it in circuits, because I'm just picturing real resistors and real wires being twisted together to be able to accomplish this.
The twisting analogy does help. I don't think I thought of it that way. Like even if I straighten it out, it still shows parallel or series.
Yeah. So the reason I say a junction is because that's really what remains, even if you bend the wires. There is a point at which the legs join each other on either side. No matter how you draw it, no matter how you twist them, there is a connection point between the ends of either resistor. In parallel and for series, there is only one connection point. So one side, one of the two legs of each resistor joins, and there's not another option. Like there isn't this third one that says charge could go this way. You can't have that for series. And this was a question from someone else, so I'm pivoting to another email I got. So go over the pinch and slide tests again, or more on how to determine whether resistors are in parallel or series in general, including any other alternative methods of checking. Which that's where I read it and I was like, people don't like the slide and pinch test. And that's okay, because again, that's not even what I do. All right, junction and loop rules, again, using the examples in the packet. So I think I touched on the previous thing. If you do want to think of it in the slide and pinch rule way, and you know what, actually, I'm going to open an old set of notes. A more detailed picture of the pinch and slide stuff so you could sort of see it in the notes in this one. I just cut it because I don't know if people actually like the slide and pinch stuff. But anyway, ignore the fact that these hands have 6 fingers. I don't know how that happened. Anyway, the slide test is, can you put your finger on one end of either resistor and slide to the other without running into anything else? Technically, if there were a battery right here, still the resistors are in series because charge has no other choice even through the battery. So the main thing you're looking for that you don't want to run into is a junction. But we typically don't give y'all circuits where there's any kind of chicanery like that going on anyway, with batteries in between. The pinch test, this might be a better sort of depiction of it. You put your fingers across one resistor, your thumbs across the other, and you just let your finger trace out the wire, and your thumb trace the wire, and then this thumb trace and trace. You're trying to be able to bring your fingers together, pinch them, and not run into anything but junctions along the way. This actually is just another way of saying, is it the same junction on both sides of the resistor, or the same junctions on both sides of the capacitor? That's how you know they're in parallel. Something like this, these are not in parallel, because if you try and put your fingers across this one, and thumb, finger, and then some kind of hand happens in between, I'm not going to draw it, I can trace this finger around, I can slide it along the wire, and I don't hit anything, and this thumb, I can sort of move towards that junction, and I don't hit anything. So I'm fine over on this side. And my thumb down here, I can also start sliding the other way. And I hit a junction, I say, all right, this is looking pretty good. But either if I imagine it as my thumb keeps sliding here, I run into something else before I get to the capacitor I wanted. Or if I'm thinking of it in terms of this finger up here sliding, I run into a different thing before I get to a junction. So it's sort of like you're making sure that the path is clear on either side of both capacitors or both resistors to check they're in parallel. I think on that, just different people will like different versions of what I've said, so take whichever you like best. All right, and then loop and junction rule. A recap on that was asked about. All right, so I think they just want me to go back through this one. So I'm just gonna start from scratch and talk through it. And you know what? I'm gonna start making up some stuff just so you can see, like, I'm not really doing anything different depending on what the circuit looks like. It can look pretty nasty, but really it doesn't actually make it much worse typically. Okay, so I'll just put some numbers to these. Let's say this is 1 ohm, 2, 3, and 4 volts, 5 volts, 6 volts, 7 volts. So this would be how it looks before you're asked to do anything. And the question would be, set up the loop and junction rules for this circuit. The batteries usually are labeled, but just in case they're not, the long side is always positive, the short is always negative. So it's not a sign you need to figure out. That's just how batteries work. They intentionally have one side at higher potential than the other. Resistors are the one where it depends which way charge is flowing through them. In the same way of, like, if water's flowing one way through a pipe, it must mean that the side it's entering is higher up than the other side that it's exiting out of. That's how water can flow through it. If water's flowing the other way, it must be the reverse, that the side, I hope you see what I mean. Like, depending on which way, if you see water flowing through a pipe to the right, it's probably because the pipe's tilted this way. If you see water flowing through a pipe to the left, it's because the pipe is tilted the other way. It's the same idea with resistors. The direction that charge is flowing is actually what tells you about which side is the higher potential and which side is the lower potential end. So let me go through these rules. And this one is sort of like Newton's laws in Physics 1. If you don't follow these steps to a T, then things will not go well. Something will fall apart along the way. If you do, even if you don't really know why it works, it does work. So, what's the first step? Set up the junction rule by labeling currents at each junction in the circuit. All right, where are their junctions? It's wherever, you could just say there's 3 or more branches, is another way to say what a junction is. So this is a junction, this is a junction. This is not because there's only 2 branches, which actually means there's no choice still. It's just something rounds a corner, charge rounds a corner. These are the only 2 in this circuit. At each of those, I'm supposed to label which way current flows in each branch, because again, that's the point of a junction, is it's where current splits off into different directions. The thing is, I don't know. Your guess is as good as mine on which way current flows without doing any thinking about it. But that's the nice thing about the loop and junction rules, is you don't have to. I'm going to just decide this is what happens. I don't know that at all. I'm making this up. And it's no problem. If I go through the motions, I go through the math, I will get the right answer up to some negative signs. And then I'll just know I drew those things that I labeled negative wrong. On the exam, I probably will just pre-label directions of the currents for you and ask you to write the junction rule based on them, but we'll see. I'm going to give these names. This is I1, this is I2, this is I3. Why? Just because it doesn't matter. And the junction rule says what about those currents?
Current going in is equal to current going out.
Yeah, so what currents flow into that junction? Well, picture those arrows as the directions people in cars are driving. Which cars are driving towards the junction and which ones are leaving it, driving away from it?
It would just be I3.
Yeah, I3 is the one that's going in. I1 and I2 are going out. Because if you see 50 cars go in and yet only say 20 go this way, 10 go this way, you're going to be like, where did 20 cars go? Where'd they disappear off to? Are they hiding in there? And it turns out for charge, it's not allowed to once you reach a steady state. A buildup or a pileup of charge would lead to, it would change electric fields, it would change how much current flows, so it wouldn't be a steady state sort of scenario. This would be like a steady flow of cars, not people parking at a junction. So anyway, that is our equation for this side. All right, let me keep reading through because it sounds like I'm doing okay with the steps so far. Yeah, whether currents enter or leave doesn't matter. Current leaving one junction enters another. Label both. So what's that about? I come back over here. If I follow this current, there's no place where it has a choice if I keep going. It just keeps flowing through different things. And remember, the battery is like, there actually is a connection. This is like a battery that charge can flow through it. And a resistor is just that thing you've seen in lab. So there is a path, but there's no splitting allowed at this stage. So I1 is what flows all the way through this branch, including right here. I2 flows all the way through this branch, including up to this junction. And then I3, if it's flowing in right here, I can sort of backtrack it and say, well, it must have been flowing like this before. And so the reason I point this out is because otherwise you might see this second junction and call it I4, I5, and I6, even though they're actually the same, and that would be too many currents to worry about. All right, let me write the junction rule on this side just to make sure it's clear. What goes in? So at that junction, what cars are driving towards it? Which ones are driving away from it? What arrows are heading into the junction? What arrows are heading out from it?
I1 and I2 are entering, and then I3 is leaving.
Yep. So this must be
I
true.
think I just overwhelmed myself a lot because it looks like a lot looking at it, and I get overwhelmed and don't realize that it is actually kind of simple.
Yeah,
Me too.
and I really think that's what it is for this particular problem, is you want it to be harder than it is in a way. Like, it doesn't feel like this is it.
Yeah, I feel like I'm missing something
Yeah.
most of the time.
And that's what I'm trying to get across is these rules are it. Like that's what's so nice about them is this really is all that you have to do to get through this process. And what I noticed is it's actually the same equation, just I swapped the order. Makes sense because what went out went into the other side and vice versa.
Mhm.
All right, so where am I at now? Okay, now it's time to label the terminals of the resistors based on which way current is flowing. It should flow from positive to negative because, again, that's sort of like if you see water flowing, you're expecting it to flow in the high side and out the low side. You don't expect water to just flow uphill very easily. So that is not what we would see. We would see if current's flowing this way, it's because this is positive, this is negative, meaning higher and lower potential. All right, so for the 1 ohm resistor, which side of it, left or right, would you decide is positive?
The left would be negative and the right positive.
So which
No,
side is current flowing
no,
in? Which is the high side?
Uh, did we start from the battery where it's positive and then like go work our way up?
What does this rule say? Current flows
based
from
on
positive to negative.
so the positive would be on the left and the negative on the right.
Yeah, that's the whole thing. Current is flowing downhill. It's flowing from positive to negative. We don't expect water to just flow uphill for no good reason. What about for
Oh,
resistor 2? Which side is the positive side?
the top side of it, and the negative's gonna be on the bottom.
Yep, because that's sort of the normal way you'd expect water to flow is if water is flowing this way, it's because this was the higher end of the pipe, this was the lower end. It would be very odd to see water flowing this way. I'm trying to even picture how to draw that actually.
It would be a lot of force involved for the water
Yeah,
to flow.
yeah, that's kind of the idea is like the charge is going the way it wants to flow in a sense once the battery has done its job. So the charge is going to try and flow towards lower potential. All right, what about resistor 3? Which side is positive?
The right
Yeah,
is hot, the right side's positive, and the left side's negative.
yep, so it's like a pipe that's like that. Water's flowing.
Does it matter about the battery because like it's between the negative and negative side of the two? Doesn't matter, right?
Does it say anything about it in this list of rules?
No.
No. This
So
is
that
it.
kind of throws me off too.
Yeah.
This is it. These are the rules.
So basically, label and the resistors, because if it's negative, it just means it's opposite.
So you said you're worried
Is
about
that
like
right?
this?
Well, like, yeah,
Yeah. Okay, well let's see what it would mean. It's like I'm going down a pipe and then I go up an escalator. That's okay. That's a thing you can do.
because the negative's repelling the other negative, so it pushes it that way. Right?
So the negative is saying which side is at a lower potential. It doesn't necessarily mean there's actually negative charge there. It just means there's less charge accumulated there. It could be less positive. So negative is kind of it's not as good of a name for it as low versus high. But that is just sort of the convention that's used. For batteries, it's because you really do get an accumulation of negative on one side and positive on the other. For resistors, it can be, or it can just be a gradient of charge, meaning lots of positive on the high side, a little bit less on the low. So I see the concern. Like I agree, it's
Yeah.
something that I would wonder about. What I'm saying is, the list is all there is.
Okay.
Yeah,
Okay.
it's as easy as it looks if you let it be.
It's just that the diagram looks scary.
Yeah, I know.
Any circuit diagram.
It does. And that's kind of why I show the analogy to say, like, it's not really if you see what it's trying to draw, which is this 3D view that we've been doing. So if I look at my labels so far, with this was positive and this was negative, here's how I would actually draw it. I'm going to kind of make this the top side. So that middle branch, that's like having an escalator in the middle. The bottom branch, so this one right here, if I look at what's happened as I move sort of with the current flow, it's like you go down an up escalator, which takes some effort. Then you slide down a pipe, and then you go up an escalator. I'm picturing this like, I don't know, like Mario or something. So on this branch, there was an escalator up, but that's after you had already slid down a pipe, which this is, best we're going to get out of me, but slid down a pipe. And then that was after you went down an escalator. So before that was some sort of escalator. And this part is a little tricky, like, how does that connect up to this? But it would just be that the thing I drew is not quite matching up. It should really be like my escalator runs across this entire thing. And then on the top branch, it is the pipe was facing down. Then you had an escalator up. And that's sort of what gets us across this branch, which it's a mess, I know, and it may not fully make sense even. But like, these are just paths. That's all that a circuit is drawing, is just the options you have for which way to go, because that's the options charge has. And like in a real device, the point of a circuit is to accomplish different tasks depending on which branch the charge flows in. You have one branch that might be for the screen in your phone. You have a different branch that might be for the speakers. You have yet another branch that might be for the little vibrating thing that actually shakes your phone when you get a notification. You have to power each of them, but it requires different things to do each of those things. So you split off into separate subsections of the circuit. That make any sense at all?
Yes.
Okay. So let's get back to where we were. So we've labeled our resistors. Let's see what it says we do next. Set up the loop rule, so the rises equals the drops, by labeling voltages around each loop in the circuit. Going from negative to positive is a rise. Going from positive to negative is a drop. This is one thing I'm missing here. I always go clockwise. There's no reason you have to. It's just for one thing to be consistent. So I will, in each loop I see, imagine sort of walking around the loop clockwise. And my job is just to report what I see. So start anywhere you want in this upper loop, but you have to stay in this loop for this trip you're about to take, this round trip. Let's call this loop 1, this is loop 2. Where would you like to start your trip in this upper loop?
The 5-volt battery?
The bottom, so like here?
Oh, to the left of it. And
Oh,
then,
like right here?
Kind of following that arrow. Yeah.
Yeah, that's fine too. Okay, so you start following the loop. You're going. What's the first thing you see?
A resistor.
Yeah, but do you see positive to negative or negative to positive?
It's going positive to negative.
So it's a
That'd be
a drop. This was in that horrible diagram I drew, that pipe that was going down. That's how I knew that. All right, keep going on your trip. What do you see next?
That'd be another drop.
Mm-hmm.
Another drop from the battery.
Yeah, and you might be like, I thought batteries were supposed to lift stuff up. Does this list of rules care? No matter the type of component. Going from minus to plus is a rise, plus to minus is a drop. Where that part comes in, the thing that's special about batteries is that they're already labeled. We didn't have to do what we did for resistors for a battery. They already have a predefined positive and negative terminal because of that lifting job that they have. Okay, we keep going. What do you see next?
The junction, but then that one in the loop at the 5-volt battery, correct?
You're glossing over a lot of stuff.
Uh,
So we're up to here. That's what we've walked through so far.
Oh, okay, my bad. My bad, I skipped ahead. Okay, and then would be another drop on the
Yep.
2 ohm,
All right, and then what?
and then the junction, and then the battery.
Well, so remember, you decided we'd start from right
Yeah,
here.
to start. Okay, so that would technically be the battery.
Yeah, so what do you see at the battery?
Okay. Right.
A rise. Because you have to get back to where you started, which you started right here. You have to pass through the battery to do that. The loop rule says the rises equal the drops. Okay, well, how do I report this? Come over here. For each resistor, you need the current through it and its resistance value. For each battery, they will give you the voltage, the difference in potential across its terminals, or I will give you, I guess I should say. So let's just go back through and see what we said. We saw 3 drops, 1 rise. How would I write this drop that I saw?
Would that be like a -1 ohm? Or
Does it say anything about negatives?
no, but
No.
I don't know. Just it being a drop makes me want to say negative.
So it would just be the current through that one, which is I1, times its resistance value, which is 1 ohm. Or if it was just left generic, it might be like R1. What do I see next?
A drop,
A drop. Of how much?
4 volts,
Yep. Okay. Keep walking. What do you see next?
another drop,
Of how much?
2 ohms,
2 ohms times the current through it. That's the special thing for resistors. How much current is through it, which is I1, and then 2 ohms. So that's the difference you see between batteries. They just are whatever the value is. For resistors, you have to say what's the current and what's the resistance. And what's the last thing I see?
a rise.
Of?
Is that 5 volts?
Yes, I'm just gonna. Yeah, it is a 5-volt rise. You are done with this loop. There are cases where, based on the labeling you did, you actually get only drops, no rises. That's also okay. What would go on this side if nothing ended up being a rise?
Would it be 0 volts?
Absolutely. And similar up here. Depending on how you label your currents, you might decide, actually, they all go out. It would be odd physically because it would be like cars popping up out of nowhere into existence and going out in every direction. But it's okay math-wise, and Kirchhoff's rules are more of like a math tool. In that case, he would say the number going out is I1, I2, and I3, but nothing goes in. So, like, these rules, they just work. This is like the first time in physics where, like, just doing it in the way that feels correct is kind of the right thing to do. Okay, let's move through loop 2. Where would y'all like to start in loop 2?
I'm good with anything.
Good, because it doesn't matter. Let me start right here. All right, I am going to make sure I always walk around loop 2 though. So this lower loop, I'm not allowed to just, for some reason, decide I want to go upstairs. I want to go to loop 1 again. I have to keep following loop 2. And let's try and
So
do
would
this.
the 5 volts be considered part of loop 2 also, because it kind of goes beside it, or is it?
Yeah, so you
Goes,
see it
okay,
as you walk through loop 2. You do see that battery.
okay.
And what is the first thing you see for this loop? Do you see it as a rise or a drop?
Junction.
Well, yeah, okay, you do see the junction. Like, what's the first kind of circuit
Drop.
element? A drop across this battery. And you might look at that and say, but I just said it was a rise. Well, yeah, because you were walking the other way.
Yep.
Yeah. Stairs look like a rise if you're at the bottom. They look like a drop if you're at the top. All right, we keep walking from there. What's the next thing we see?
Another junction, but when you come around to the 7-volt battery, it will be positive to negative to that drop also.
Yep. A drop of 7 volts. All right, keep going. What do you see next? Let's try Eva. What do you see next?
I see resistors, and it's going from, is that positive to negative?
Yes.
So another drop of 3 ohms, and then also the current is I3, I believe.
Yep. So it is a drop of I3
I3
times
and
3
3
ohms.
ohms.
Yep. All right. And what's the last thing you see?
It's a rise of 6 volts.
Yep. You are done with loop 2. And there is a third loop. There is just this whole outside. It is actually going to look pretty similar to these two because it's sort of what you get if you add those two loops together in a real mathematical sense. But you're free to if you want to practice it. But this is it. That's all this is.
That actually helped a lot.
Yes.
Yeah.
That did help. Yeah. It's mind blowing.
Yeah. Well, and I mean that is the amazing thing is like circuits seem like hieroglyphics when you first see them. It seems like some arcane knowledge that for some reason some people know how to use and others don't. But like it is this more or less. It's just routing charge to different things that you need to power up. That's maybe not giving enough credit to electrical engineers. They do work magic with this tool set. And I will say, so we have 3 equations for our 3 unknown currents now, so you could solve this in principle, but again, I wouldn't make you. I just need the 3 equations.